Hello, welcome to Fundamentals of Acoustics. Today is the fourth day of this current week, and today we will start discussion on poles, zeros and their plots, and also Bode plots, which are very helpful in understanding the overall asymptotic response of linear time invariant systems. And all these concepts will be heavily used as we delve deeper into the realm of acoustics. So, it is important that we understand these concepts, review them, and from next week onwards we will be actually starting to get into concepts related to acoustics, and all these concepts which we have been reviewing over this week and also the last week, they will be very useful for for developing a detailed understanding of acoustics. So, what I plan to start discussing today is pole zero plot. Pole zero plots. So, we have seen that a linear time invariant system, it will have a transfer function, and this transfer function will have a numerator, and the numerator can depend on complex frequency S, and it will also have a denominator which will also change with frequency, complex frequency S. So, both the numerator as well as the denominator, they could be functions of complex frequencies. So, both the numerator as well as the denominator, they are algebraic expressions in complex frequency. So, what that means is that I can factorize the numerator into its linear factors, and I can also factorize the denominator into its linear factors. So, let us say the roots of the numerator, we call them z. So, the roots, so the linear factors of the numerator could be s minus z1, s minus z2, s minus z3, and it can have a lot of linear factors. It depends on how complex the numerator is. If it is just a linear term, then it will have one root. If it is quadratic term, it will have two roots, and so on and so forth. And similarly, the denominator will have roots, and its linear factors will be s minus p1, s minus p2, s minus p3, and so on and so forth. So, these z's, z1, z2, z1, z2, z3, and so on and so forth, they are called zeros. Okay, they are called zeros, and they are roots of numerator. When complex frequency approaches or becomes equal to one of these roots, corresponding to that complex frequency, the value of transfer function becomes 0, unless it becomes 0. Similarly, the poles, so the roots of the denominator P1, P2, P3, and so on and so forth, these are called poles. So, these are roots of denominator. The roots of denominator. So, when the complex frequency becomes equal to at least one of these roots of the denominator, then the value of transfer function at that complex frequency becomes infinite. So, at poles the transfer function becomes very large, at zeros the complex function, the transfer function becomes very small. becomes approaches 0. So, let us do an example. So, Hs is equal to S plus 2 divided by S square plus 5S plus 4. So, the numerator is linearly dependent on S and the denominator is a quadratic function of S. So, now what I can do is I can factorize the numerator. So, numerator is just S plus 2 and the denominator is S plus 4 times S plus 1. So, what that means is that this transfer function has one 0, z1 equals minus 2 and it has two poles, p1 equals minus 4, p2 equals minus 1. So, I can plot these poles and zeros on a pole 0 plot. So, this is again a complex plane. So, real axis, imaginary axis and 1, minus 1, minus 2, minus 3, minus 4. So, I have a 0 at minus 2. So, I designate 0 by this circle and then I have two poles, one pole is at minus 1 and another pole is at minus 4. So, this is a pole. So, this is my symbol for pole. So, this is a pole 0 plot. What is the purpose of this pole 0 plot? If I have a pole 0 plot for a system, then from that pole 0 plot I can very easily construct the transfer function. Okay. I can very easily construct the transfer function. Of course, there may be a scalar factor, some phi. That phi I cannot estimate from a pole 0 plot, but whatever is inside the brackets that can be deduced from the pole 0 plot. And once I have the transfer function, I know how the system is going to behave as its frequency changes. For a given input, what is the output going to be, I can compute from this transfer function. So, just one graph can give us the whole information about the entire system. So, this is the importance of pole 0 plots. Let us do another example. So, in the first case, all the poles and all the zeros, they were located on the real axis only, but that may not necessarily be the case always. So, let us consider this system Hs equals S square plus 4 divided by S square minus 4S plus 13. So, the roots of the numerator are S plus 2j and S minus 2j, and for the denominator we will compute that. So, for computing we do roots of denominator So, this is a quadratic expression in x. So, S equals minus, so the thing is S square minus 4S plus 13. If I have to find out its roots, I have to equate it to 0 and then I compute its roots. So, this is equal to plus 4 plus minus b square minus 4ac. So, 16 minus 4ac minus 52 divided by 2a, 2. So, I get 2 plus minus 3j. So, the function becomes h of s equals s plus 2j and s minus 2j divided by s minus 2 plus 3j and s minus 2 minus 3j. Okay. So, now we write down the roots of numerator and denominator. So, z1 equals minus 2j, z2 equals plus 2j, p1 equals 2 minus 3j and p2 equals 2 plus 3j. So, this system has 2 poles and 2 roots, and we will plot them on the complex plane. So, that is my real axis, that is my imaginary axis. So, this is 1, 2, minus 1, minus 2. So, first I am going to plot the poles or the roots. So, one root is at plus 2j, other root is at minus 2j. And so, these are zeros. So, these are the 2 zeros, and now I am going to plot the roots for the denominator, which are poles. So, it is 2 plus minus 3j. So, 1, 2, and this is plus 3j, this is minus 3j. So, this is one pole and this is the other pole. Okay. So, this is one case where the poles and zeros are not necessarily on the real axis, but they are somewhere in the complex plane. So, that completes our discussion on pole zero plots. The next thing we are going to discuss is Bode plots, and I think it will be better that we start it tomorrow. So, with this we conclude the discussion for today, and tomorrow and day after tomorrow in the next 2 classes we will cover cover the concept of Bode plots. Thank you and have a great day.